Hello, hello. So today we're going to cover unit binary search. So today's going to actually be a pretty short meeting. Yeah, we're just going to go over binary search. Now, before we start, let me just quickly cover the curriculum. As of before, we've already covered everything in the bronze section, right? Last time we finished the binary search tree and then divide and conquer. So everything up to that point, all of the bronze session, technically this is one session. So theoretically speaking, 16 to 20 hours of class materials here. All right, so that's the general class pacing. And silver would technically be session 2. Now the structure of silver is depending on the unit. But as you can see, some of the units are pretty similar. Right? Binary search, dynamic programming, recursion, sort. These are all concepts that's covered in the first section. And because of this, there are not a lot of new slides, not a lot of new concepts. A lot of these problems, it uses the same concepts, but it's just that the problems are more difficult. All right. And we're going to see that today when we look at the binary search projects. So yeah, let's get started then. Binary search. In binary search, so yeah, like I said, today's going to be a pretty short meeting. Binary search, the first project is called first bad version. First bad version this is just a recap of how binary search works, right? It's just simple binary search, this project is. So basically in this project, supposedly you have n versions of something, right? And then you are given an API, you're given an API and then basically it returns you that starting from which version does the version become bad. And this, in this sense, this works, the premise for this is, once you have created a bad version, right? Let's say you've created a bad version for a product, then every following version of that product after that bad version is going to be also going to be a bad version. So the goal of this binary search project is that given this list, you want to find out what is the bad version, right? What is the first bad version? So right here is an example. Supposedly you have 5 versions, and then the bad version is 4. So the output will be 4 because starting from version 4 is because if you call the function on 4, 4 is the first instance in which is bad version is true. And every instance afterward is where first bad version is false. So that's the idea. And so the code itself is pretty simple. Right, you're given so this many numbers, right? So you have this many versions, and then you just do recursion on it. I mean binary search on it. You set a start and an end, and then while you're still looking through the loop, while start plus 1 is smaller than end, you find out the middle point. And then if the middle point is a bad version, then you set the end to the middle point. Otherwise, it says start equal to mid. You may recall that this code is actually really, really similar, or it basically is the exact same as the problem in bronze, the binary search bronze project called first position of target. And the idea is the same, right? You want to find the first position of something, which is basically what's going on here. You want to find the first position of the bad version. All right. And so that's why you set n equal to mid, and then when it's done, you just return start if it's bad version. If the position start is the bad version. If not, return end. All right. And that's it. It's a pretty simple code. This project is just meant to be a quick recap of how binary search works again for your students. And again, it's really similar to the code for first position of target. The next one, more difficult, is called, let's go back to silver, is called search in a big sorted array. So for this project, the problem here is assuming you're given an array that's really, 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 really big. So big such that you cannot get the length of the whole array. So you know, in binary search, it's important to really for it to work is you need to find a midpoint. And how do you find the midpoint? To find the midpoint, you need to find out what the starting point is and what the ending point is, right? And then you know, do some math to find out what the mean is and find the midpoint. Without being able to access the length of the whole array immediately, we cannot find the midpoint immediately. So how do we find the midpoint then? That's a problem. And then the key here is really everything built after this line is the same. This is just regular binary search. The key is this line right here. We need to find a way to get to the end of the array really quickly. And then if we just loop through it one by one, like if we just like count, it's gonna take forever because it's already given that the array is so big, we cannot get the length of the whole array immediately. So instead what we do is we set n equal to 1. And then while the end is smaller than the target being, you know, the number we're looking for, while the end is smaller than the target, because we don't know what the end is, we're counting, right? While the end we're currently looking at is smaller than the target, we multiply it by 2. And we just keep multiplying by 2 and 2 and 2 and keep going until we get to a point where this end we're looking at is bigger than the target. Once we get to a point that's bigger than the target, then, you know, we can just use binary search on it, right? Because if you think about it, we don't need to find an end point that's at the really end of the array. The goal here is to find the index of the target value, right? So as long as the end value is after the target value, the end index is after the location of the target value, then we're good. So that's why this works. And this idea also, you know, matches this idea of, you know, binary search in the sense that we're multiplying it by 2 so that the time complexity is not going to be O(n), but instead O log n, which, you know, a lot faster. After that, everything here is going to be the same as regular binary search. And now the last thing we're going to cover today, the median of two sorted arrays. Slightly more difficult, more difficult. So in this project, you have two sorted arrays called num1 and num2 with two different sizes. One size is m and n. Now, the idea is, given these two sorted array, we want to find what is the median of the two sorted arrays. And the overall time complexity should be O log n plus n. All right. So let's say we have a line, let's look at this product one, like 1, 3, 2, right? The first array is 1, 3, second array is 2. We want to find the output should be 2 because 2 should be the median. So how do we do this one? You can see that we use this, someone uses recursion here, but really it's not, yeah. Well, okay, so to do this problem, we're going to use binary search because we want to optimize it. Obviously, we could, combine the two arrays and then sort it, and then after we sort it, call binary search on it again. But if we do that, the time complexity is going to be way bigger than O log n plus n, since we're going to have to sort the array first. Not going to do that. The idea then is there are basically, you want to break it down into different cases. So first, the bigger two cases is one, what if it's a if the total number of values is an odd number right here, we just need to find the median. If the total number of values is an even number, then we need to find two medians, right? I mean, the 2 points that the two values that are smaller and bigger than the median, and then average them to find the median, right? If that even like 1, 3, 5, 7, the median is going to be 3 plus 5 divided by 2, which is 4. Now, well, let's break down the helper function. So how the helper function works is it uses this binary search concept of every iteration you remove half or you remove part of the array you're looking at. This way you don't have to look through the whole thing, but you look through part of it. All right. So we have a few things. We're given the parameters are going to be the num1 array, the starting number we're looking at, the starting index of the num1 array we're looking at. So in the beginning, it's going to be 0. Num2 array, starting index on num2 array, and then IDX, just index. All right. So these two cases are if if the nums1 array is empty, then we just need to find the medium of the nums2 array, right? Recall that IDX at first, okay, IDX at first is going to be the length of the whole thing. Right? IDX at first is going to be the length of the whole thing. So, yeah, if the num1 array runs out, if num1 if num1 is yeah, if num1 is empty in a sense empty, then we just need to find the medium in the nums2 array. If nums2 is empty, we just need to find the medium in the num1 array. Right, that's the idea. Otherwise, if that's not the case, we're gonna come back to using these two cases later. But if that's not the case, then we're gonna be looking at this stuff right here, right? We first find, so here, like there are like a few different cases here, and I'm gonna simplify it, but I really recommend to really understand this, really we can just look through all the different cases and then break it down, draw it out by hand or whatever. So you first find like a halfway point. And the halfway point would be the minimum between either the let's say the length of the first of nums1 array, length of the nums2 array, or the middle point of the or like the half of the total length. So think about it this way. What's really going on here is you have two arrays, right? And then so if you and then you know the halfway point of the whole thing. You know the halfway point of the whole thing, and you know the total amount of array. So then if you compare, no, not if you compare, then you know there are a few cases such that in the first case, the first array has a smaller number of values in the second array. Second case, the first array has more values in the second array. Right, not comparing the actual size of the numbers inside, but just number of values in there. Third case, you have the same number of values, right? And then so basically what's going to happen is you look at the halfway point. If the halfway point is a smaller number, otherwise if you loop through the whole thing, if the length of the arrays are going to be bigger than the halfway point, then we look at the halfway point, right? If the halfway point is if at the halfway point the number for the value corresponding to nums1 is smaller than numbers corresponding to at nums2 at that halfway point, then we know that everything before this value per se, everything before this value in the nums1 array is going to be in the lower half of the sorted array. It's this value, right? Must be one of the smallest k numbers in the two sorted arrays. And in this sense, we know that everything before this then cannot be the median. And then so we just call the helper function again. And then we basically do this right here, add half to it. And then we just ignore, basically just ignore the numbers, these numbers. And then we recursively call this function again and then look through it. And that's it. All right, now, interestingly enough, really, if we look at you can look at a few simple cases. So let's say we have let's say we have the nums1 array to be smaller than the nums2 array, right? And also all the values in there are going to be smaller. There are a lot of different cases, but let's look at this case. All the numbers in there are smaller as well. So then the halfway point, then if that's the case, right, then the minimum is going to be the nums1, the length of nums1. If the number of values in nums1 is smaller than the number of values in nums2. And then so this value right here will basically be like the last index of nums1 array, of the nums1 array. This value right here will be the biggest index on nums2 array. I mean, no, one of the values in nums2 array, that's at that point, right? And then so since this is a case, right, since we know that assume that everything in nums1 array is smaller than nums2 array, and this is a case, then basically we just know that we just basically ignore all of the nums1 array. And then we subtract this value, the number of values in the nums1 array, from half. And then since then, at this point, the nums1 array has run out, we just do this right here. And then we just return how many numbers are left from that half starting at the nums2 array. And then we find the median. So a bunch of different cases that just go through, let's go through these cases, and then you'll see that this works. All right, so that's it for this one, median obtuse sorted arrays. And that's basically it for today. Now for next meeting, I'll put out an announcement in ThinkLand. So it's just here. Let me put it out here. I'm not sure if I'll cover any new materials, mainly because so far we've covered all of bronze, which is all of session 1. So instead what may happen is I'll put on an announcement, I'll put it right here. Next one, instead of a one for content, I may do like Q&A and just go over what the evaluation topic is and how evaluation is going to work. And that's it. Or I may just combine that with the Python AI one together on like a Saturday or Sunday or whatever. But yeah, I'll put out an announcement here, and all the recordings are going to be available in the Zoom video recording. And in terms of evaluations, all the evaluation video information and the sign-up link are going to be emailed to all of you. So, all right, so that's it for today. Thank you for coming. If you have any questions, feel free to stay after. Otherwise, bye. See you next time.
Bye.
Bye. Thank you.